Dobar večer, dobar
Okay.
večer.
Okay. So,
Čujete me, dobar večer. Mjau, mjau.
so we are now back for the last two lectures of this Zagreb part of the conference. We are pleased to welcome Professor Branko Grisogono from Department of Geophysics in Zagreb. During the last 30 years, he is developing very successful career in meteorology, not only in Croatia but also in Sweden and United States. And the title of his talk today is What do climate models and we know about Bora-like windstorms? So, Branko, please. Welcome.
Thank you very much, and thanks for holding on this long day. So I'd like to talk about climate modeling on progressively smaller and smaller scales, and going to something what is, let's say, Croatian brand, which is Bora wind. Although Bora wind blows in many areas in the world, a few dozens of places, Croatia is known as like the origin of that kind of flow. Mostly I'll talk about strong and severe Bora flows. So basically we continue on geophysical fluid dynamics, that we had several talks today on that. And that means that belongs to theoretical physics, and that is strongly linked to applied mathematics. Going to climate, what to say about climate? Climate is a collective state of the atmosphere, including its surface, monitored or modeled or observed over a certain period of time, 30, 50, or 100 years, over certain areas. Or if you want to say it in a more lay language, then you would say climate is what you expect and weather is what you get. To acknowledge my authors, some come from these departments, some are my former students. They all ran away from me, of course. And some people are from already now in Germany, Croatian Weather Service, and or mechanical engineering and naval architecture. This view is from the highest weather and climate station in Croatia. That's a place called Zavižan, 1.6 kilometers above sea level and looking out toward Italy. And the reason why this island over there is totally bald, this is the island of Pag, is because of Bora wind. Bora wind is a strong, severe downslope windstorm. We heard a couple of talks today, especially from Professor Collins and some others, on climate regional perspective. Here I'll progressively scale down, and I'm very happy that I'm not putting my equations, that I took them away, because they show at most of the equations that we are talking about here. I'll just give them their names. Another name for this topic could be, let's say, partial differential equations applied to geophysical fluids. That would be equivalent to this. So background, Bora flow is intrinsically dynamic flow. It's not thermally driven as it was thought, let's say, 30 years ago. When I was a PhD student, I was taught that was a thermally driven flow, like katabatic flow. If you have a surface, you cool the surface, then the air here is heavier than the air away, and that's why this air would sink down. This is a very minute, very small part of Bora flow. This is not the case. Bora is mainly dynamically driven due to orographic waves. Orographic waves are waves produced by mountains, sort of similar like waves in the ocean. If one should pick one single dimensionless number to describe that flow, that is given here, this is this Froude vertical number, and some people who don't like that name can call it inverse of the dimensionless mountain height. U is the background wind speed, this one, N is buoyancy frequency, and H is the mountain height. When this number is less or equal to 1, then orographic waves have difficulties to pass over the barrier, then they eventually break. So there are two competing effects: the jumping over the mountain and breaking, and the other effect is to go around mountain and fly over the flanks of the mountain. If this number is very high, let's say 5 or 10, then the flow is linear and you don't have wave breaking. So essential mechanism for severe Bora or hurricane speeds Bora is wave breaking. These speeds, by the way, can go to 40 or 50 meters per second, and gusts may go to 70 meters per second. We don't really know what's the real speed because the instruments typically break. We haven't observed much of the speeds above 75 meters per second. So as you see, I'm going toward progressively smaller scales. I will not talk about synoptic setup, regional setup, how it happens. It will just go by side. And I'll go to progressively smaller features, which are pulsations in the flow, certain semi-periodicity in the gusts of Bora, then rotors. Rotors are horizontal vortices. It's kind of like a snake rolling this way, kind of like very dangerous for air traffic, for bridges, and so on. And turbulence. And turbulence is notoriously difficult even to explain what it is, even to give a definition. It's kind of like, let's say, pornography. It's not easy to define it, but once you see it, you know it. It's there, yeah. So similar is with turbulence. Going on climate models. We heard several talks today on climate models. Essentially, those are primitive equation models. What does that mean? Those are three-dimensional hydrostatic equation of motions. Conservation of mass, thermodynamics, conservation of water, and so on, and lots of parameterizations solved numerically. What it means hydrostatic, that means one of the components of motion is not calculated prognostically. It's only horizontal or semi-horizontal component, often called U and V. They are prognostic. While demanding hydrostaticity means that pressure and buoyancy are all the time in a balance, and vertical velocity is not calculated prognostically in such models. That is okay for larger scale models that have a resolution, let's say 50 kilometers or 100 kilometers. Those are large climate models. And in their vertical velocity is calculated diagnostically, let's say from mass continuity. That means that it must be instantly fulfilled. It goes by infinite speed, this adjustment for vertical velocity. So vertical velocity does not have its memory in hydrostatic models. What does mean parametrizations? Or space is solved, differential equations are solved, let's say, in such boxes or such boxes, finite differences, and any signal that has, let's say, 5 or 6 elements of such calculation, its wavelength is more or less resolved. So that's explicitly resolved calculation. Everything between that is not resolved, or it's poorly resolved, or partly resolved. So it's almost terra incognita called, and those processes must be parameterized because they are important, but we don't see them. What is there? Let's say small-scale turbulence, precipitation, clouds. They are very important, but we can only treat them in a kind of statistical way. So here I go on a particular model, RegCM, which is built essentially in Trieste, in ICTP, International Center for Theoretical Physics. It's basically made of a mesoscale model called MM4, MM5. Here is a reference. Equations you can pull out on the internet. You just type RegCM, you download the documentation and everything there, which kind of Unix system you should have on computer, how much space, and so on and so on. So we'll now a little bit go on that, and that's together with our PhD student, Ivan Gittler, who just published the paper, and Georgi is one of the top climate modelers here, and he is also the last author on the last paper here. So next, I'll show you errors of such models, so that we trust too much to our models, I think. So this is going to be critique to climate modeling things. On the right-hand side, I'll show something which is first-order turbulence parametrization closure results, and on the right-hand side will be higher-order turbulence closure scheme. Everything else will be the same. So I'm using same resolution, same dynamic core, same type of clouds, same type of radiation, everything but turbulence parametrization. What is that? Turbulence parameterization, for instance, this here is Reynolds averaged covariance of fluxes. U is in x direction and W is in vertical. So this is parameterized diagnostically. You prescribe sort of K value. Here, this is K for momentum. Either you calculate it locally through some gradients, or you calculate it non-locally, prescribed profile, and you multiply with the, let's say, gradient of the given wind. That's one way to do it. And also has no history. On the other side will be a prognostic turbulent part, only its part. So this is essentially a tensor thing. This is a Reynolds stress tensor, which measures fluctuations, turbulent fluctuations in the flow, and their divergences, their inhomogeneities may produce acceleration or deceleration. Typical way to do it, that then you say that eddy diffusivity, Km, eddy diffusivity is proportional to the turbulent length scale, capital lambda, and square root of turbulent kinetic energy. Turbulent kinetic energy is the trace of this tensor, so it's basically just the diagonal part. That's the only part which is calculated prognostically. Everything else is diagnosed to speed up calculation. And lambda is one of the weakest points in whole theory, and people just use it. They take it for granted. Lambda is like a measure, statistical measure of most energetic turbulent eddies. And that is very elusive quantity. Very, very kind of spiritual thing. It's taken from molecular physics. It's like mean free path, but for eddies, you cannot talk about that. This is rapidly moving, fast, jumping process. So now come a couple of figures. On the left-hand side, again, those are errors from model I mentioned, RegCM, using first-order turbulence scheme. And on the right-hand side are errors with higher-order turbulence schemes. One could claim that higher-order turbulence schemes on the right-hand side are perhaps slightly better. Here you have measures of mean average error and mean error. The top panels are for December, January, February, and the lower panels are for summertime, June, July, August. And below it says that those are temperature near surface, 2 meters temperature errors using first order closure or higher order closure. Red is positive errors and blue negative. The main message to take from this complicated figure is that most of errors happen either in mountainous areas or in coastal areas. Errors are kind of colors are agglomerating, accumulating in the mountainous or coastal areas. Look, for instance, around the Apennines, around the Alps, around the Scandinavian mountains, and so on. So this is the message to take away. Better turbulence parameterization scheme just made a minor improvement. Next one, same, organization of picture same as before, but this is for wind speed. Again, largest errors happen either in coastal areas or in mountainous areas, and these parts are poorly treated. Mountain resolution, model resolution is again only 50 kilometers. For the rest of my talk, I'll focus on the area here in the Adriatic, opposite from Italy. I'm sure that most of you know where it is and that you went there swimming. Maybe you'll learn how to swim there. I'll show you some of the data at the Adriatic coast. Most notably here from Seine. Here is town of Seine, well known for Bora flow, this black square. Next one is Vratnik Pass, 700 meters above sea level. We'll look for the flow toward the island of Krk. This is island of Krk. And Bora blows from northeast here toward the coast. So here typically there is a high pressure system and or low level pressure system in the Mediterranean or Adriatic Sea. This is a large scale setup. But here we are looking for details. And typically Bora flow is here better defined than when you go down south. New measurements we have from this area in the hinterland of Split, and soon I'll show you a picture from here. Aircraft data I will not have time to discuss here. And then we'll do some numerical modeling and see how that goes. Here is a sketch taken south of city of Split, which oversimplifies the Bora flow, what it says. The full line shows typical wind profile with Bora, where speeds go to 10, 20, 30 meters per second. The dots show profile of turbulent kinetic energy. Secondary maximum aloft is not shown here. That is associated with orographic wave breaking. This is just for the surface, for the engineers. And here then happen in the lee of the mountains, cascade of orographic waves and Kelvin-Helmholtz waves and pulses and turbulence happens there. The view is down the road from Split to Dubrovnik. Well, that's the nicest one I had. So next one, we are back to the Zavižan station, the highest station up there, and this is a little bit of history. Only in mid-80s it was found that Bora is not thermally driven katabatic flow. If you click on Google, on internet, you will find wrong messages that Bora is a thermally driven flow. It was only in mid-80s shown that Bora is really a severe downslope windstorm, typical, that one that blows similar to Föhn, dynamically similar to the wind Föhn, and Boulder and Denver severe downslope windstorm. And in 90s started finer numerical modeling with a resolution of 8 kilometers, insufficient for fine scales, and now we are doing better and better measurements there. Unfortunately, remote sensing is missing because it's very expensive. Remote sensing means like very fine radars there. Another view from the station, and what you will see soon, that the areas where happen low-level jets, those are like high-speed wind, like when you open a water in a bathtub, and then wakes correspond to mountain gaps, mountain passes, or mountain peaks. And typically such structure during the Adriatic coast happen every 10 to 30 kilometers. Oops, that went a little bit wrong. Excuse me. We are here, yeah. And this should be... presenter should not be too jumpy, huh? Yeah. Here are satellite data from high elevation, so-called SAR, synthetic aperture radar. It's a kind of holography of a sea surface, and you can see much of agitation of the sea surface. On the left-hand side is a mediocre type of Bora, moderate to strong Bora, while on the right-hand side is a severe Bora case from February 2012 when much snow happened in Split. When in Split, I think it was like 950 broken legs and hands. I don't know how many were casualties in Rijeka, but it was happening a lot all over, and it was minus 15, minus 20. That was the coldest weather in 2012, and we called that case all over Bora case, severe wave breaking that went for several days. Here is a record of Bora measurements in Seine, 1 second data with a running mean average here. And then if you take, let's say, 6th hour here, just expand it, and here you can see pulsations. The thick line on the right-hand side show you pulsations. Those are semi-periodic oscillations in Bora that may last between 1 to 12 minutes. How to model that? You have to go to progressively finer and finer models. Such models are still not used for climate research. Eventually they would be. It's almost as before, with a big difference that now you use non-hydrostatic models. That means vertical velocity is calculated prognostically. That means that you don't necessarily demand that the pressure and buoyancy are in a balance in the vertical. Another parameterization set is included for radiation, for clouds, typically for turbulence. And also compressibility is allowed too. So different numerical schemes are used. Let's say Marchuk schemes for time splitting, which is like semi-implicit and so on. They are fast, efficient, but they over-smooth the data. So there are some problems with that. Here I'll go on 2 models here. They use, again, as before, terrain influence coordinate frames. So this is non-orthogonal frames. At the surface, they follow terrain. And higher they go, let's say to 50 millibars, 20, 30 kilometers aloft, then they become semi-horizontal. and then various projections in horizontal. You may use Mercator's projection and so on. COAMPS is turbulent parametrization scheme. These typically use, again, forecast of the wind variance, which is just the diagonal of the former tensor, which is basically TK times 2, which means Reynolds averaging. COAMPS, that's coupled ocean atmosphere model, developed mostly in Naval Postgraduate School, Monterey, California. And the other one, which is now widely used, it's totally open domain, it's WRF. It's Weather Research and Forecasting from Anchor, Boulder, USA. So next I'll show you some results from very fine resolution, horizontal resolution of 333 kilometers. And next one will go all the way to 1100 meters. Those are exceedingly fine scales, and that almost goes to so-called large eddy simulation modes, although these models are not large eddy simulations. Former models, one that I showed results, had 50 kilometers horizontal resolution. The official model for Croatian weather forecast by the Weather Service, called Aladan, uses 8 kilometers resolution. So please know that this is 20 to 40 times finer. So when we torture our PhD students, we let this simulation runs for 2-3 weeks, and maybe they don't never get PhD. Yeah. Here is a sketch of a typical pulse, but taken directly from numerical model, because I want to sketch first what you are going to see in simulations. This is a sketch goes from A, top left, to D, down right, and by 100 seconds, 100-second steps. Darkest color, you see its highest wind speeds over 37 meters per second. The white is below 29 meters per second. And the solid curves is so-called potential temperature. You may think of it's a combination of density and ordinary temperature. The value should be higher up. If you see some kind of turning and overbreaking, that's direct symbol that waves are overbreaking there. So what you see here, one pulse here is dying out, and the pulse capital A is building up. Here capital A is growing up, former one here died, a new baby one is being born here, pulse B. In figure C, pulse A is in its mature phase, and it's going to die soon before it comes to the island of Krk. Here is island of Krk, and here is the town of Senj. And the final graph, 400 seconds apart, so it's like 6-7 minutes. Pulse A is dying out, and pulse B is coming into its mature phase. This is called Bora pulsation, those semi-periodic moves. Here you see on 111 horizontal resolution, each minute taken a slide. Up here we look at the photos from aloft. Here is Zavižan. Here is the Vratnik Pass, and on the left side is the island of Krk. Upwind side, you don't see very much activity. Then the flow accelerates uphill, which is direct sign that this is a dynamically driven flow. It's not thermally driven flow, because flow would not go up there. And then you can see areas of low speed, tongues of low speeds, blue, and red and dark red speeds over 36 meters per second. Those are hurricane speeds, by the way, passing out over the sea. This is the model second level at 10 meters above surface. So solving Navier-Stokes equations with turbulent kinetic energy included here. On this resolution, basically, this parameterization should not be valid, should not be used. Here aloft you see the time. Here is now 1740, so it will go back for 3 hours, minute by minute. Because on this fine scale, 100 meters, one should not use this type of higher order turbulence parameterization schemes, because they suppose that all turbulence spectrum should be modeled, while on this scale you already resolve some of the spectrum. Therefore, this is kind of double counting. You already resolve some of the turbulence and you parameterize it. So fortunately, on this scale for Bora, there is not much left on this scale. So nature is nice to us, although this is, mathematically speaking, this is not the proper way to do it. But this is the way how people do it, and they publish papers, yeah. Even I reviewed this one, yeah. Okay, just before we go, next we take a cross-section here from the island of Krk, a little bit below 45N, toward east, toward Senj, and we take a vertical cross-section. So town of Senj is nearby here. Here is the island of Krk. So you see high pulses of the flow. This goes again minute by minute, 3 hours cross-section, high speeds. So it's called shooting flow. So it's like a few hundreds of meters, very high wind speed. All of that is a tremendous shear. Tremendous shear happens just a few hundred meters aloft. You see rapid changes of colors here. Although I'm color blinded, but I see there are many colors here. And aloft, dark colors, dark blue, that means almost stagnant air, moving 1 or 2 meters per second, but highly turbulent. There is happening wave breaking. Wave breaking, jumping, and in 3D, this is an intrinsically 3D phenomenon. So as the air goes over the mountain between Vela Kapela and Velebit, waves steepen, overturn, eventually break, and then this spillover happens out. More out over the sea you go, this is a kind of area where hydraulic jump happens. It's not well defined. Hydraulic jump is where the flow suddenly decelerates and jumps out over. Now the hour went over. And you see very important, strong stagnation here. Speeds go here from, let's say, 30, 40 meters per second, and here they go only to 5 or 6 meters. So it's almost as a boundary layer separation. There is another case, next one nearby Split, I'll show you boundary layer separation and much better defined hydraulic jump. Hydraulic jump here is loosely defined. Very dangerous for aircrafts. What is the cause for those pulsations? In this particular case, it took us 3 years to show that the source were Kelvin-Helmholtz instabilities. Kelvin-Helmholtz instability is a type of evanescent waves that happen when there is much shear between two different layers. Sometimes on clouds you may see very nice wave-like turning over thing. That's Kelvin-Helmholtz. But there are other possibilities. Another one is due to mountain wave breaking aloft, that you saw it with very low wind speeds. There happens vortex tilting and twisting. This is basically like this. So this is 3D effect. Eddies, it's like can I break this? No, I won't break it. But if you tilt it very much, and now you just kind of like, so that can produce these pushes and pulses which are similar to pulses that we observed. And this is a 3D effect transported down toward the surface. And then there is a third mechanism that we know that can happen, which can be both, either 2D or 3D, that there happens sort of waveguide between, here is the mountain, and here goes very high wind speed. Here is wave breaking. Here goes 5 speed. This is low speed. And then between the wave breaking, here happens waveguide. So that can be 3D or 2D. Here is the sea. And other cases seems that happen, and we don't know what happens when it's combination going on. Now, toward the end of my talk, we go down more south. You see here toward the hinterland of Split. Here we have measurements there. It's nearby Dugopolje. Split Airport happens to be just over here. Split is here. And this is not our PhD student. Those are professional climbers. Above 10 meters, you are not allowed to let your workers climb up there. Yeah. But the bad PhD students is very welcome to go up there. There are 3 levels where we have very fine measurements over 1 year of data. Nobody in Europe, nobody in America, I think, has such unique data sets with 5 hertz continuous measurements there. Here, of course, I show the best case, measurements at 20 meters, blue color on the left, and red is WRF that I showed you before, numerical simulations at 20 meters elevation and using horizontal resolution of 333 kilometers here with prognostic turbulent kinetic energy. So here is the tower where we have measurements, and soon you will see through this cross-section also airflow for 1 hour how it goes. Here it goes. This is between 12 UTC and 1 UTC. The time is written upper here, or here you can read. The measurements are done here. This is the Pometeno Brdo. Here is a Split, and Dinara Mountain is out here. So pulses are not only produced here, they seem to be advected out over several kilometers. You see, this is over 20 kilometers. And then they come to the last mountain here, and then here is the boundary layer separation. You see, the speed here goes offshore, and here goes onshore. So this is a boundary layer separation, internal new boundary layer. I believe it's associated with sea breeze, that already developed sea breeze, and these pulses are elevated higher up, and they get transported in the mid-troposphere, which is one very efficient way how to bring turbulence into free atmosphere. Free atmosphere is everything above boundary layer, everything, let's say, above 1 or 2 kilometers. And such pulses can exist for several hours, and then they can disappear. And that can be associated with the jet stream aloft, and there are so many details that are missing in today's climate models. Another important parameter for Bora is its anisotropy. So here we just calculate the standard deviation of the vertical component here versus horizontal component, U and V. Very naively, one would expect that this ratio should be around 1, especially for Bora flow, which is nearly neutrally stratified. Strong stratification happens aloft here where wave breaking occurs, but down here there is almost no stratification. However, we found very high anisotropy for Bora eddies. On the lower panels there are 3 spectra shown from here, 40 meters, 20 meters, and 10 meters. Arrows show so-called spectral gap, that energy should be on one side on mesoscale or large-scale motion, on the left-hand side of the spectrum, and on the right-hand side should be, like, say, turbulence. And black curve corresponds for U component, which is this down the hill, and then the other one is V, lateral component, and dashed is a vertical component here. In all these cases, we managed to find spectral gap, which is important for Reynolds averaging to hold. Otherwise, if you don't have spectral gap, your averaging, your statistics is not based well. And we found pulsations. You see, on 8 minutes, we found pulses, not only for Seine, we found in Dugopolje. So this is, like, say, brand new results which is just waiting for peer review literature to go. Of course, you have to survive reviewers. Yeah. Here is a histogram of various speeds in the hinterland of Split, with various times of averaging. This averaging is not a proper averaging. This is called running mean averaging. And we know that running mean window is not a very good low-pass filter. So low speeds here correspond for this very long episode of 3 days of Bora, for onset and cessation of Bora. The second maximum, here around 12, 13 meters, shows that this is just moderate to strong Bora, average maximum speeds, but the last maximum are pulsations. And they are not accommodated for in climate models, even in weather models. So dealing with pulsations is a sensitive thing, and in climatology this is not addressed yet. We don't know when it will happen, because engineers need, for the bridges, for cars, for airports, they need very, very fine statistics. What would be, let's say, pulses? What is the return period for certain processes? Climate models are just deaf. They don't know. So to start wrapping up, there are other issues that we are working on. One thing is anomalous refraction of radio waves. What happens with the Bora, that there is a strong cooling in the lower layers, and then warmer air is aloft, which changes the radio signal's ray refraction. And that can corrupt communication. American military pays for such things very much to study such effects, because that can affect rockets to be discovered very, very too late when they are approaching a certain ship and so on. And here we, of course, only think for music from Italy to come over to hear stuff. Then air pollution, what happens with ozone, with volatile components, with NOx, all these important features are nicely related to Bora flow. How much air comes from Gorski Kotar over Lika, because that also changes photochemistry. It also affects what happens in the river of Po in Italy, if they get or air or pollution goes there or back. Recently we worked with a new generalized Z-less mixing length scale. As I criticized before, that the mixing length scale in turbulent model is one of the weakest points. This is kind of like a rubber gum, and everybody stretches as much they need in the model without much physics. It's typically like experimentally based. So what we claim that should be related to turbulent kinetic energy, which is just, when you take a square root of TK, this is just local turbulent speed. Corresponds to that. Capital S means for shear. Wind shear is important. Richardson number is a certain ratio between buoyancy and shear, and Prandtl number is kind of ratio between eddy diffusivity and eddy conductivity. So several parameters should be inside there. Whole Mediterranean area is having progressively more problems with fire protection, and such regions should have areas there. Agriculture, olive trees, vineyards, what would happen where, and future Bora scenarios are rather vague. We don't really know how much Bora we will have in, let's say, in 50 years. Will it be more seldom happen but stronger, or it will be more often but weaker, or both? There are different opinions nowadays. And to sum up everything, I really think that climate models don't see severe Bora flows, and there are two reasons for that. One is insufficient resolution, because if you don't resolve process, it's very difficult to parameterize it. And even if you parameterize it, so subgrid scale, treated statistically, mechanisms are so complicated. They are so different there. So I think we will come there earlier with our better resolution than what we would be able to parameterize that. And here I would like to stop and maybe entertain your questions.
Thank you for this really nice and interesting lecture. Are there some short questions or comments?
No, it's not my cat. It's a Hungarian cat.
Okay, maybe I think the best would be to leave this discussion to the round table. So I would like to thank Professor Grisogono again. Please.